All right, this lesson, guys, it's the fundamental theorem of algebra, and as it relates to polynomials, we're going to learn about, like I said, we're going to put everything together, think about the graphs connected to the roots, connected to the x-intercepts and the factors, and what everything means, all right? Try to make sense of everything and make some connections here. This lesson puts it all together for us. So hopefully, and again, lesson 37, we're moving on. We're moving on to another part of the course, okay, totally different. Moving on to exponents, and it's nothing to do with polynomials, okay? So let's make sure we try to do a good job here of understanding. This is a very, very important lesson, everything put together. Okay, so in our opening exercise, we're just going to factor. So we already know how to factor, right? We're going to do this real quick. X plus 9, x plus 3. Okay. Here we have x plus 4, x minus 4. These are things we should be able to do in our head. That's why I'm doing them quick here. X squared plus 16, we just did this, right? It can't be factored with real numbers. You have to use imaginary numbers. X plus 4i, x minus 4i. Okay, hopefully you remember that from our other lesson. How about this one? Can't be done with real numbers, and it's going to be, now I don't really know the factors off the top of my head. What it'll give me 5 and 4, but what we can do here is we can pretend it's an equation, and we can use the quadratic formula to help us. So you want to factor something like this. You can do the quadratic formula, even though it's not an equation. It'll help us get if we can get the solutions, then we get the factors. All right, so negative b plus minus 16 minus 4 times 5 over 2. And you see how it's going to be imaginary. Negative 4 plus minus radical negative 16 minus 20. So negative 4 and then over 2. So this is going to be, you got to kind of write small here. 2i, so negative 4 plus minus 2i over 2, and then divide by 2, negative 2 plus minus I. Negative 2 plus minus I. So that means one of my, let's think about what this means. We have to write it up here. One of my solutions, if it was an equation, would be x equals negative 2 plus I. And the other one would be x equals negative 2 minus I. We kind of talked about these in lesson 35, how you would handle those kind of roots. As factors, which is what we want factors. As factors, how would we write these? Oh, I'm stuck. Okay. As factors, how would we write these? Well, this one would be x minus 2 plus I. And this one will be x minus 2 minus I. You always do the opposite, remember, because it's, if you treat it like this, they're, oh, no, it's not. It's negative, sorry. It's minus 2 plus I minus, so negative here, negative 2, negative 2. Okay, so we're going to have one factor will be x plus 2 minus I, and the other one will be x plus 2 plus I. Those are your factors. Okay, so your factors will have I in it. Your solution will also have I in it. But the polynomial does not have I. All right, so exercise here. We're going to go through an exercise, step by step, A, B, C, D, E, whatever, E, F, G, H, okay? And then we're going to go through an example, one example. One exercise, one example. Looking at the graph, how do we know that there is only one real solution? Try to answer this without me giving it to you, right? How do we know there's only one real solution? Well, you should know that the real solutions are the x-intercepts. So there it is. Looking at this graph, there is only one real solution, the x-intercept. The x-intercept is the real solution, And that'll be 1, right? X equals 1. is it possible for a cubic polynomial function to have no zeros? Can a cubic, the cubic does this, can it have no zeros? Well, the answer is no. A fourth degree could have no zeros because a fourth degree could come down, come back up, go down, and then go back up, like a W. Down, up, and it doesn't have to hit the x-axis. But a third degree goes down forever and up forever. Our end behavior is negative infinity to positive infinity. So this is impossible to have no roots. So a cubic polynomial must have at least one. Must have one x-intercept. Okay? So the answer is no, I guess. No. From the graph, what appears to be one solution to the equation? Well, we already did it. X equals 1. I did it a little early. Okay. How can we verify it's a solution? Well, we can verify it's a solution by plugging it in. So we can do P of 1. P of 1 equals 1 to the third plus 3 times 1 squared plus 1 minus 5. And that'll give us 1 plus 3 plus 1 minus 5, and that'll give us 0. So P of 1 equals 0. Remember, P of each x-intercept, P of the x-intercept should give us 0 all the time because the y is 0. All right, so that's how we would verify that it is a solution. Moving on, based on this solution, what is one factor? Now this is where we're going to get a little creative. Not really creative, but it's kind of like putting together what we already know, right? We know that, so we know that x equals 1 is an answer, a solution. So therefore, what's one factor? Well, you just change the sign, right? We talked about that. So we know that x minus 1 is going to be a factor of this, right? If we know that x minus 1 is a factor, we could find solutions. Right here we're going to find solutions. So we're going to say x minus 1 times what? What's left over? Factor out the expression you found in that. So this is how you're going to factor it out. Remember back, and I said we're putting a bunch of different stuff together in this lesson. Remember we did synthetic division? Synthetic division takes us, and we kind of did this earlier in the year, even this part. Synthetic division takes us from that third degree down to our second degree polynomial. We already know one factor. So synthetic division, that's what we're going to do here. Let's do synthetic division with a 1, because that's our root. So you got 1, 3, 1, negative 5. Okay, so do our synthetic division, and we get 1, 1, 4, 4, 5, 5, 0. We got to get that 0. And then remember, these right here are the x squared, the 4x, and the 5. These are the coefficients of our quadratic. So that's the leftover. That's the leftover, x squared plus 4x. So it's going to be x minus 1, x squared plus 4x plus 5. Okay? Now, what are the solutions? Well, I already know one solution, x equals 1. But how do I get the other solutions? Well, I have a quadratic now. So now I can use the quadratic formula. See, the point of this is if you can use nice rational, not only rational, but integer solutions to get factors, and then the rest of the factors can come from the quadratic formula as long as you use synthetic division to get down to a quadratic. You have to get it down to a quadratic first. So now we can use the quadratic formula here. X equals negative b, so negative 4, plus minus, and it's going to be 16 minus 4 times a times c over 2a. So that's going to be negative 4 plus minus radical negative 20. Oh no, 16 minus 20, radical negative 4 over 2. And, look what's happening. It's this. See? X squared plus 4x plus 5. That's why we did this opening exercise. So we know it's going to come out to be negative 2 plus minus 2i. Negative 2 plus minus I. Oh, this was 2i. Oh, did I make a mistake up here? 2i. Oh, no, I. Yeah. So it's just I. Oop. Just I. Negative 2 plus minus I. Okay, so now write it in terms of linear factors. Okay, so I can do that. I can go x minus 1. And then I did it above. X minus negative 2 plus I. And x minus, parentheses, negative 2 minus I. And that technically is good enough. Those are your terms of linear factors. Linear meaning there's no squaring going on. Okay, so there is linear factors. X minus negative 2 plus I and x minus negative 2 minus I. All right. Exercise 2. Write each polynomial in terms of linear factors. Okay, so this isn't going to be bad. So we have x times x squared plus 5. So this one's not too bad. We're going to have x, and then this is going to be x. Well, let's solve this. X squared plus 5 equals 0. Or do our quadratic formula, but this is easier. Negative 5, square root, x equals plus minus I radical 5. All right, so I have x minus I radical 5 and x plus I radical 5. So x minus I radical 5 and x minus negative I radical 5. So that's going to be x plus I radical 5. So there we go. And here, so here I have x. I'm going to take out x minus 3. Oh, well, for this one here, I'm not taking out x minus 3. I'm sorry. We have a common, we can do it by grouping. We can do this one by grouping. So we could have x squared here. And that's going to be x minus 3. And then 4x minus 3. So that's going to be x minus 3 times x squared plus 4. And then that's x minus 3. And then we know x squared plus 4 is x plus 2i, x minus 2i. All right, so there are your linear factors. X minus 3, x plus 2i, x minus 2i. That brings us to the fundamental theorem of algebra. The fundamental theorem of algebra has two parts. Part 1 says that you always have to have at least one solution. Okay, at least one r such that p of r equals 0. So there has to at least be one x-intercept. All right, if the degree is greater than or equal to 1. In the part 2 of the fundamental theorem of algebra, and this is kind of confusing, but basically what they're saying is every polynomial can be written in factored form. X minus the first root, x minus the second root, x minus the third root. So essentially the fundamental theorem of algebra is that every function can be written in factored form, essentially. That's basically what it's saying here. Okay, so we're going to do that. We're going to do a example here, and then we'll be done. So part 1 of the fundamental theorem says that this equation will have at least one solution in the complex numbers. How does this align with what we can see in the graph to the right? So because you see how it's a degree of 4, this can't be, this only has 2 x-intercepts. So because there's only 2 x-intercepts, it's 4th degree. Therefore, you must have, and we only have 2 real roots, 2 real solutions. We must have 2 complex solutions. Okay, so if you have 2 real solutions, you must have 2 complex solutions because there's a total of 4. That's basically what the fundamental theorem of algebra is helping us with. So identify one 0 from the graph and use the 0 to factor out one linear term. All right, so we can do that. We know that we have 1 and 2. 1 and 2. So I already know x minus 1, and I already know x minus 2. are going to be two of our factors. So to factor one of them out, we're going to use synthetic division. Doesn't matter which one you start with. So let's start with the 1. And then we'll go, let's see, our coefficients are 1, -3, 6, -12, 8. So I have 1, 1, -2, -2, 4, 4, -8, -8, and 0. All right? So now I'm down to 1, -2, 4, -8. And we have a cubic polynomial, x to the third minus 2x squared plus 4x minus 8. Again, these are the coefficients for the cubic polynomial. We started with 4th degree. Now we're down to 3rd degree. We use the 1. Now we're going to use the 2. We did this a little bit earlier in the year. All right? So now let's do another one. 2. Okay. 1, -2, 4, -8. All right, so we have 1, 2, 0, 0, 4, 8, 0. All right, this is going to be x squared plus 0x plus 4. So I have x squared plus 4 equals 0, because there is 0x. And I already know this can be factored. It says, are we done? Can we factor this out? Yes, x squared plus 4 can be factored. X plus 2i. See how we're breaking it down? X minus 2i. X plus 2i, x minus 2i. So look what we did. We started with a 4th degree polynomial. We used the graph to get 2 real roots, 2 real factors, 2 real solutions, right? And then we used the synthetic division to get it down to a cubic. We used synthetic to get it down to a square, where we could now factor it. X plus 2i, x minus 2i. So now write it in factored form. This can be written in factored form. X minus 1, x minus 2, and then we have these guys. X plus 2i, and then x minus 2i, and that equals 0. How many solutions? The solutions are x equals 1, x equals 2, x equals -2i, x equals positive 2i. So 1, 2, and then plus minus 2i would be your solutions to this equation. We will practice it more in class tomorrow. See you then.